if you look at any textbooks in fluid mechanics, right, you will see that, you know, irrespective of who has written it, okay, you will always see these different class of problems that are being discussed. Okay, I think Sumesh has already discussed about, you know, your pipe flow, right? Plus we have also done, you know, this is a concentric cylinders, right? You have two cylinders, one inside the other, so that problem also has been done. Okay, and then you will also see problems where there are two plates. That means, you know, you have one plate at the bottom, one plate at the top. Okay, and then the top plate is rotating. So there are, you know, there are cases where you kind of come across problems like this. Okay, in the case of concentric cylinders, what happened was you had a cylinder, you had an inner cylinder, and there was a way of rotating your inner or outer, right? Depends on what kind of devices you want to deal with. Okay, and so this geometry is called a parallel plate geometry. What you have is you have two plates. Okay, and I actually have an example of something like that. So this is, if you're interested to know a little bit more about it, you can come to our lab. So we have these devices. So this is actually a kind of a shaft to which at the bottom you have a plate, right? You know? And then there's going to be a bottom plate. I'm just going to keep, you know, this configuration, and your fluid is going to be filled between the plates, okay, the bottom plate and the top plate. Okay, and there's a way of rotating this. Okay, that is, you know, this parallel plate geometry. Okay, oops, yeah, okay, that's your parallel plate geometry. Okay, another example is something called as a cone plate geometry. So again, you know, there's a similar device like this. Instead of a flat plate here, it will be a tapered cone. Okay, and again there's a bottom plate. Okay, so these are four class of standard problems that you do in different books. Okay, pipe flow, plate, cone plate, and concentric cylinders. Okay, now when you do these problems, okay, I mean, all of you know the classic way to approach these problems, right? You write, you know, momentum balance, you know, all of that, right? So you kind of know how to get the flow fields, you know, all of that, right? Now when you do problems like this, what is your thought? Do you think these are very academic oriented problems, or do you think there are some applications of these things? There are some applications. Okay, what would those applications be? How do you think we can use some of these geometries that, you know, you guys learn, you know, in every course, you know, or every course in fluid mechanics? How do we use them? Okay, that's going to be the reminder of, you know, the today's, you know, lecture. Okay, so I'm going to show you some examples of how you can actually exploit, you know, some of these things for measuring a few things. Okay, so that comes to, you know, the measurement of viscosity. Okay, okay, so so of course there are several devices for, you know, measuring, several ways of measuring viscosity of fluids. Okay, in my opinion, one of the most versatile, you know, instrument which can be used for measuring viscosity, not only viscosity, a lot of flow properties of materials. Okay, because if I take, for example, like say syrup, okay, versus ointment, right? They're very different, right? Okay, one easily flows, other one doesn't flow, right? Now when you have complex materials like that, okay, you will see that, you know, I can't use something like, say, devices that are typically meant for measuring viscosity of fluids cannot be used, of course, for the measurement of, you know, flow properties of ointment, right? So in that context, rheometers are one of the most versatile devices which can be used for a range of samples all the way from liquid to solid, like, you know, for example, toothpaste and ointments and stuff like that. Okay, so and of course there are a lot of different flow geometries that people use, but three most commonly used geometries are kind of you know, mentioned here. That's your parallel plate, cone plate, and your concentric cylinders. Okay. Again, if you want to know how to use it, if you want to see the instrument, you can of course drop by the lab. We can show you a few things as well. Okay. Let's just look at now. So when I say that these geometries are kind of used for measuring flow properties, there is some, you have to do something. What I mean by that is that, so Sumesh talked about, he showed some videos, right? The videos were, if you had like say concentric cylinders, okay, there was fluid in between them, right? When you are rotating, you talked about Taylor number, right? When you're rotating one of the cylinder at a very low, rotation speeds, it looked like the flow was all laminar, right? And at some point there were some instabilities and stuff like that, right? Now, and of course, when you do flow problems related to this, okay, we said that you kind of assume some conditions that whether your VR is 0 or V theta is 0, you have to figure out, right? Now, when you work with these geometries under specific conditions, okay, what I mean by specific conditions is that if you choose geometries of appropriate dimensions, okay, then it turns out that the flow field that you generate, okay, in the fluid, that is in the gap, okay, between these geometries, is very well defined, okay. And for one to use rheometers, that is the most important criteria, okay. What I mean by that is, if you're trying to use concentric cylinders, okay, if you talk about Ri, which is the radius of the inner cylinder, and Ro, which is the radius of the outer cylinder, it turns out that all these well defined flow fields are going to be generated if the ratio of Ri versus Ro is very close to 1. That means that is at the limit of a very, very narrow gap, okay. So therefore, the point that I want to make is that you would have to work with geometries of appropriate dimensions, okay. Only then you develop a flow field, okay, which can be described by some of the math that you have done in the class, okay. That's the most important thing, okay. Okay, so and typically these measurements are done, as I said, right? There's a basically a shaft, okay, and so only thing that you control during your measurement is that you basically control the rotation speed. That's all you do, okay. There are some ways by which I can tell the instrument, and I can say, hey, you rotate it at a particular rotation speed, okay. That's the control that I have, okay. And in terms of the measurement, okay, what the instrument basically measures is, it measures something called as a torque, okay. There's something called as a torque sensors, okay. Whenever some things are rotating, right, you can think about the generation of the torque, okay. This instrument has something called as a torque sensor, and it basically accurately picks up what the torque that the instrument is applying, okay. And this is common for any geometry, whether you use a parallel plate, or a cone plate, or a co-ed geometry, okay. So the configuration is clear to you guys, right? So that's your your rotation speed, right? And m is basically the torque that you're that is being measured, and of course Ri is the inner radii, inner cylinder radii, and Ro is outer cylinder, and that's your length, okay. So this is so basically this is a geometry of well defined dimensions, okay. That's all I wanted to say, okay. Now, so now when you have some cylindrical object, okay, when it is rotating, okay, now what I can actually obtain is what is the shear stress, okay, what is the shear stress that the wall of the rotating cylinder is facing, right? Or what is the shear stress that this rotating object is feeling, right? And so now if I know, so you know that this is your torque, okay. Torque divided by distance will give you the force, right, okay. Now your tau r theta is the shear stress that is being applied onto the your cylindrically rotating geometry, right? Okay, because it's a function of r and theta, right? It's independent of z, right? No matter, because that's your z axis, right? And it's rotating like that. Okay, so what you are basically measuring is at the wall of the rotating cylinder. Okay, your shear stress multiplied by the dimensions, okay, is going to give you your force. Okay, therefore, if I basically know, because I'm measuring mi, which is the torque that I'm applying, I have a way of calculating what is the shear stress. Okay, right? Because I know what I'm applying, I know the dimensions, I can get your tau r theta. Now you worked out the your in the previous a couple of class ago, right? You worked out expression for v theta, right? Yes or no? You did, right? And you kind of got this expression that it depends on there's a mistake here, right? So it has to be capital R. So right. So basically it depends on your rotation speed, or inner radii and outer radii, and your radius, right, is a function of r, right? Now you can go back and actually find out that so whenever you do a fluid flow problems, you got to think about shear stresses, right? And shear stress is a tensor. There are 9 components, and depending upon the problem that you're dealing with, some are going to be 0, some are going to be non-zero. Okay, so what I've done is I've taken an expression for tau r theta, from one of the standard books. Okay, and because I know v theta, okay, I know that this is 0, right? So I can actually substitute for v theta, I can actually get tau r theta. Okay, I'm going to give these slides so you don't have to write it down. Okay, okay. So I can substitute for v theta and I can actually calculate tau r theta. Okay, and tau r theta, right? It goes as mu times all these parameters. Now I can evaluate this tau r theta at either Ri or Ro, depending upon whether I'm rotating the inner one or outer cylinder. Okay, I can actually evaluate tau r theta, right? Now because I already know what tau r theta is in terms of the torque, I can substitute that into this equation. I can actually measure what's your viscosity. Okay, so all that is done in these devices is that there's some way of correlating the torque that the instrument measures, okay, into the shear stresses. Okay, and if I know the shear stresses, I can actually back calculate what my viscosity is. Okay, and similarly you can also again your shear rate, okay, would also depend on your your average radius, the rotation speed, and and inner and outer cylinders. So basically what I can do with these devices is I can take a fluid, okay, I can put them in the gap between the cylinders or the bottom plate and the top plate. I can just change your the rotation speed, I can change both the shear stress and I can also change the shear rate. I can measure viscosity at every value of shear rate and shear stress. I will get information about how does the viscosity is changing as a function of shear rate or shear stress. Okay, that's what is done in a rheometer. Okay, any questions? Okay, so there are other devices, right? I mean, rheometer, as I said, is one of the most versatile devices for doing what is called as rheological studies or flow behavior of materials. Okay, and there is also something called as a falling ball viscometer and something called as a capillary or a U-tube viscometer. In this capillary viscometer, what is actually exploited is the fact that you have a thin capillary and through which a liquid is flowing, and that is a classic case of flow through pipes, right? So basically whatever equation that you develop in flow through pipes is going to be kind of useful here. Okay, in the falling ball viscometer, what you basically have is a liquid column. So that's your that's your a spherical object, okay, typically a steel ball or some other material. Okay, and that is there's a column of liquid, that's the liquid is filled in this column, and of course it has to be a constant temperature bath, because you know that viscosity is a function of temperature as well, right. So right, and then what you do is you make this object fall in the fluid, okay, and of course you're going to learn a little bit more about it whenever you have a fluid that is falling in a a column of, whenever you have an object which is falling in a column of fluid, okay, and if the fluid is stationary, okay, so you can think about writing a simple force balance, okay, and there's a net gravitational force acting on the particle, which is your gravity minus buoyancy, and there's a drag force, okay, so you can put up expression for each of these things, and so therefore you can actually ultimately get an expression for something called as a terminal settling velocity, okay. That means, so the moment you drop this object in the fluid, initially there is some acceleration, okay, at some point the ball is going to move at a constant velocity, and that constant velocity is basically governed by the balance between the net gravitational force and your drag force, and we know that your drag force depends on your viscosity, right. As it falls down, the presence of the liquid basically slows down the ball, right, and therefore so what you can do is I can get this terminal velocity, and if I have some way of measuring terminal velocity, if I know what is the radius of the diameter of the ball that I'm using, okay, if I know what is the density of the particle, density of the fluid, if I have some way of measuring ut, I can actually get the viscosity, okay. So simple concept, okay, but people still use, I mean there are commercial instruments available which kind of exploit this technique, okay. Okay, so and it turns out that this is this particular approach you can only use for cases where the expression that I took for drag force, okay, that's what is called a Stokes drag, okay, and that is only true if your Reynolds number is less than 1, okay. So therefore this only works if you are working with very small particles, okay, or very small objects, okay. If I take like say meter sized spherical objects, if I make it fall, it's not going to work, because you have your diameter of the object in the numerator, it's going to be really large number, okay. This condition is not going to be satisfied, therefore you would have to work with appropriately small dimension objects, okay, and then you would have to ensure that it's in the what is called the laminar flow conditions, okay, and that's when you can use this, okay. And how do people measure? So what they will typically, the instrument would look something like this, right. I think I had shown this here. So there's basically the central column that you see here, right, that's okay, that's your fluid column, okay. Now there are some graduations in the column, okay. Now it turns out that when you want to measure, you're going to have this experiment in the lab next semester, okay. The objective would be you drop a ball, okay, and you look at the velocity of the ball at different sections, okay, in the column. It turns out that if you plot the velocity as a function of time, okay, it's going to increase initially and it's going to remain constant, right. That's when your terminal velocity is reached, right. So therefore I would have to have some way of measuring velocity of the ball that is falling at some successive positions, okay. So there are markers, okay, there are markers like that, that's a graduation that you see in the ball, okay. Now if what you do is you basically identify at what is the instant of time at which, okay, the ball intersects this ring, okay, and what instant it basically travels and goes outside this ring, okay. Therefore in that sense it will travel the distance that is equal to the diameter of the particle in some time, right. So therefore I have some way of measuring what is the distance it travels, okay, and what is the time that it has taken for traveling that distance, right. So basically this expression, okay, and I can measure what the distance it travels, and that's your length, time, right. And because these are all constants, okay, so everything is constant, I can actually write it as a k times rho p minus rho times t, Okay. Now your rho p is kind of kept here because depending upon the kind of fluid that you're going to work with. Okay, you may be working with objects of different materials. You can have a steel ball, glass ball, and things like that. Okay, so in that sense, you can. So basically, your viscosity, is actually some constant k. That is something called as a ball constant. Okay, it depends on the properties of the ball and things like that. Okay, and okay, so you measure the time and you basically get your viscosity. Okay, that's how the falling ball viscometers work. In the capillary viscometers, what you do is you have some blobs, right, something like that here. Okay, right. So what you do is you basically fill these blobs with the fluid of known volume. Okay, and then you basically find out what is the time that it takes for draining out. Okay, okay. So again, the working equation is something like this. Again, you can derive this. So your V by T, which is the volumetric flow rate. Can anyone recognize this equation? Does it look familiar to you? Was that correct? Right? Poisson equation. Now, I don't know if we did this in the class. You kind of derived the velocity profile for the flow through pipe, right? Now, if I know what is the velocity profile, there's a way of getting your flow rates, right? You would have to, integrate the velocity profile multiplied by your area, right? So you can basically get your flow rate. Okay, that's your V by T. Okay, so volumetric flow rate. Okay, and so now if you look at this equation, there are actually two things, right? One is your delta P, okay, plus your rho GL. Okay, there are two contributions to the pressure drop, right? One is because typically these experiments are done in a vertical column. Therefore, I would have to also worry about your hydrostatic pressure as well. That's why you have this term. Okay. Now, when you're working with capillaries, okay, your pressure drop across the pipe becomes important when you're working with pipes that are really large in size, right? When the length of the pipe is really large, your delta P becomes appreciable. But when you're working with a capillary, when you're working with small distances, I can actually neglect that. Okay, and I can say that the pressure drop purely comes from your hydrostatic effects. Therefore, your V by T basically goes as rho GL times the pi RC power 4. That's RC is your radius of the capillary, and your viscosity and the length. Okay, if I know the length of the capillary, if I know the diameter of the capillary, if I have a way of measuring your flow rates. Okay, so basically I can substitute all of this and I can basically get your viscosity. Okay, so what people typically do is you can express this as some instrument constant times rho times T. Okay, where instrument constant, what you do is if I have two fluids, okay, I can calibrate my instrument. I can actually get the instrument constant. Okay, so yeah, that's all I wanted to say today. Okay, so basically the point is that there are different fluids, and depending upon what kind of fluids that you're dealing with, they exhibit different fluid properties. Okay, and there are devices for measuring viscosities. Okay, and you should be aware of some of these things, and some of these things you're going to use it in your next semester's lab. Okay, so maybe with that I'll end. If you have any questions, we can take them.